t dt. And you have f of t is 1 over twice pi integral f of omega e to the plus j omega t d omega. This is actually the form you know. For those of you who had something to do with image processing, you have a similar definition of the Fourier transform, maybe with slight difference, so that the here minus, here plus, in the special Fourier transform you switch. So you have, say, f of kx and ky is double integral f of x and y. Actually, it is here plus x kx plus y ky dx dy, and f of x and y is 1 over twice pi squared f of kx ky, and you have here e to the minus j x kx plus y ky dkx dky. Okay, this is the one-dimensional spectral or temporal spectral, and this is the two-dimensional spatial spectral too. So the kx and ky, they are called wave numbers or spectral wave numbers. They play the same role like the frequency for time signals. Okay? If we look to this here, maybe I put it also in minus, but I should have put it here in plus. I mean this in order to be consistent with the standard definition. It's important if you work with both, with kx of xyt, to obey this here, because a wave phenomena, if you have propagation in plus direction, you have omega t minus kx. So it's important to keep one plus for time, minus for space, or the other way around. Okay, now regarding spares sampling, or what is called compressive sampling. Imagine that for time signal now, imagine that you have a sine omega t or cosine omega t. If you look to the time domain, it is something which continues forever. And if you apply Nyquist now, say, okay, blindly, I will sample, and I have no idea about the nature of the signal itself. But if you perform a Fourier transform, you will find out that this infinitely long signal is just Dirac, or if it is finite width, maybe sinc function. Okay, and if you look to sinc function, what you need for sinc, you know now it is sinc. You need the magnitude of the main lobe and the first zero, and that's all. Okay, so you need just two pieces of information for a sinc function. Okay, exactly the same here, and exactly also in an area of the signal processing which is called compressive sampling or sparse sampling. It is the same. If you know, and it is very, very well known, maybe for those of you who are involved in communication, it's very, very well known in communication, because in communication you send predefined signals. So you don't send any signal. For mobile communication, for Wi-Fi and so on, you send well-defined signals. So you know the signal which you send. Okay? Therefore, you can make use of some attributes, some characteristic of the signal, in order to reduce the amount of information you need. And this is called compressive sampling. So instead of sampling according to Nyquist, you say, okay, no, I will sample much less. The advantage, of course, is to have speedy signal processing and to reduce complexity, and you have lots of advantages. Exactly the same here. Let me first come back to this form here. Originally, we have a phase which is linear function of x, and a frequency which is linear function of y. But this is not yet kx and ky. If you now substitute epsilon of y here and theta of x here, you see that because of the linear dependence, it is something like constant times x. Of course, you can take this constant term outside the integral. This is not important. But you have a linear function x times kx and a linear function y times this, the whole one, let us call it ky. Okay? Now, you ask yourself, I would like now to collect information, collect information in the spectral domain, in kx, ky, because if I perform the inverse, I need a two-dimensional net or two-dimensional distribution of spectral points. Spectral mean in the kx, ky plane. Now if you look here, what is kx? Kx was the x ramp, because in the x ramp, let me, if this is the x ramp, say this is kx, and this is x. In the x ramp, what you have done is you switched on the x ramp for a certain time in order to allow for speeding, for dephasing. Okay? Now you compare between the most right point and the most left point. If you apply a strong ramp after a fixed time, you have maybe a phase difference between, say, plus 45, from minus 45 degrees to plus 45 degrees, say. Now you may apply the x ramp for a longer time. You will have more or stronger ramp for the same time. Usually the time slots are fixed because you have a patient who moves and so on, so you don't want to play with the time. So in this case, you will play with the ramps. Okay? Now, if you look to the value kx itself, it is the slope of this ramp for a fixed time. For a fixed time, it is the slope of this ramp. So each individual value is a slope of a ramp. Okay? So this is actually the information we gain in this direction. So this is, say, kx negative. So in this case, we will have something like that. Kx equals 0, kx. So for producing the spectral data, you need a number of different ramps for a given time exposure of these ramps. This is clear? So in this case, I gained this column, this column, this column of data, of spectral data. I got a question from one of the ladies here that she was a little bit confused about the relation between these points and the spatial points. Nothing to do, because we are still working in the spectral domain, so there is no any correlation between this point and a point on my liver here or on my stomach here. No correlation. These are the spectral data. Okay. Now coming back to this here, to the how can I gain spectral data for y, ky. Either I measure at a fixed time, each time I just take a snapshot, and I make exactly like the same with x, so using, it would have been stupidity, of course, to say, okay, I will measure, I will wait after 1 minute, and then I will measure, and I will change ky dash. This is slope in y. No, I will not do it this way. I have another parameter which can change the values of ky without the necessity of having different ramps in y. So I will just apply one y ramp and make use of the t variable to produce the spectral values in the y. So is it clear? So in this way, so this is one ramp, different times. One ramp, different times. So the time plays now the role of the values of ky. This is the case of no idea about the image. If I have a priori information, I can make it spare. Spare, of course, will save time, because if I can save, say, this is time. If I use many, I may use the same time window with a speedy processor, which can measure at different times. Or economically, I will enlarge the time window of acquiring the signal, but with, say, slow processor. Again, the time window itself is crucial, because I would like to make my image as fast as possible. So in this case, the price I pay for more points here is speedy processor. Just the price I pay here, it is a repetition of the whole process, because each column here is a complete round. Excite the layer and make the X ramp and Y ramp and so on. So this is clear. And now different factors will play roles. Speed, so how fast the processors are, how long can I wait, or can the patient wait, and so on. Yeah? Okay, so therefore people try to solve the problem. Of course, here you didn't save anything. It's just another representation. I will have my spectral values in radial coordinate system. Again, this is not your cross section here. This is a spectral. And here it's a little bit sparse. Why does it take this form? This is typical to the proposed process, because all these are taken away from papers. So some guy comes and say, okay, if I make it this way, I have advantage in this hardware. I can save this processing, I can save this time, and so on. So don't ask me now what is the specific meaning of that. This is method related. So someone comes with an idea, and he says or she says, okay, this is maybe less processor or less whatever. So therefore, I just wanted to show you just some examples of how to make it sparse, how to perform less number of measurements. There are also other aspects to be discussed, which are for you, just to refresh your information. Delta kx, this is the resolution in the spectral domain. Do you remember what is related to that in the X domain? The sampling theory tells us the sampling rate is inversely proportional to the bandwidth, right? Inverse it. The delta omega in the frequency domain is related to the what is called field of view. In this case, again, you have less sampling or high sampling rate, so less time samples means higher bandwidth. Let us try to interpret this here. Many readings in kx with very nearby readings means that the corresponding y window or x window field of view is wide. So you may be content with say this one, this one, this one, this one. This will save time, but at the same time, what do you pay with? You pay now with the field of view. It's exactly like Nyquist and so on. Just think about that. So we may reduce the number of samples, but we will have a lower field of view in x and y direction. So just take all these aspects into account. The lecture here is not dedicated to these details, but just to let you think about what are the different effects. Okay? The spectral readings, the relation between the number of points, the separation between the points, and all this has also impact on the resolution, the field of view, and all this stuff. Any question related to that? I hope that this is now explained clear enough. If you oppose, just let me know. Okay, let us come now to the main point of the whole technology or of the whole system, which is related to us as RF engineers. This is what is called RF-Coil. In many applications, you use the same coil as a transmitting coil and as a receiving coil. The two coils have different requirements. In the transmitting coil, you would like to flip or to excite a cross section. And therefore, and you would like, this is something like the flashlight in the camera. The transmitting coil, this is actually the excitation. It's like illuminating your face, and I would like now to take the photo. So the transmitting coil works like the flashlight. So what do we need from the flashlight? As homogeneous as possible. Because I don't want to have only my nose here is bright and here they are dark. So the illumination. So therefore, the requirement needed for the transmitting coil as homogeneous as possible. I also mentioned that the only circularly polarized field in one direction is relevant, is responsible for the flipping. Now you may ask me, should I design a circularly polarized array or coil? The answer is not necessarily, because even if you excite linearly polarized, everyone knows that linearly polarized can be decomposed into two circularly polarized, one in this direction, one in this direction. And the only one is interacting with the spins. The other one is dead, is not there. The only factor here, you inject power. And now you inject, say, 1 kilowatt. And because of the decomposition, you lose half of it. Because only one half, which is related to the proper one, will be used. And the other one is not used. So it's not used in the illumination. As if you have a flashlight with two sides. So you would like to, so it lies in this direction and this direction. Now you flash with half of the power in this direction, the other half is produced, consumes energy, but is not used. Therefore, you should pay a little bit more attention in order to have a mechanism for purely circularly polarized, or at least say 80% in the proper circularization or circular direction and 20%. These are all our design components and design factors and reasoning what is better than what. This is now for the transmitting. So I would like to have as homogeneous as possible for the proper polarization and as much proper polarization as possible. If it is not there, it is not bad. You can image, but you pay with something. Pay with more power or something like that. Also, don't underestimate as engineers. I assume that 99% are engineers. So we are not only scientists, we are engineers. Engineers mean so we take care of power consumption, of costs, because if you invent something which is extremely very expensive and go to Siemens or go to Philips and say, okay, I have a very good coil here, say how much? No, thank you very much. Technically, it could be very good, but economically or financially, you can forget it. Good. So how does a coil look like? I would like to discuss maybe at the beginning the bandwidth of the coil. You have already seen that the bandwidth itself dictates the thickness of the layer. In the transmission regime now, I will come back to the receiving regime. The thickness of the layer or the resolution in the z direction is determined by the bandwidth of the exciting signal. One of the factors affecting the bandwidth is for how long do you expose. You have limited time, so this is a must. So the bandwidth depending on the time of exposure. Another one is the coil itself. If I have a high Q coil, I have a coil which produces signal with high spectral purity. So one of the aspects in designing such a coil is to have it high Q, low loss. So I would like to have it around F0, which is a Larmor frequency, and with as less bandwidth as possible. But how less? Because you may have a very high Q. Don't forget that using the ramps, you are also moving in a range, because with the frequency coding, you come from here to there with a certain bandwidth. All these are aspects to be considered in your design. You would like to have a high Q in order to have better resolution in the z direction, but not extremely high Q in order to have a bigger field of view in one direction or in the other direction. So these are maybe contradicting requirements. So let us take now the keyword high Q. So all components which are to be used should be low loss components. The most famous form of a RF coil is called bird cage. It is like the bird cage, as you see here. It's composed of rods distributed uniformly and connected by two rings. Those of you who have some idea about magnetostatic and so on, you can prove that if you let current flow along the rods, it will produce a circularly polarized field in the middle if the spatial phase difference or angle and the electrical phase are correlated. Let me explain what does this mean. Imagine that you have four rods, one at theta equals 0, theta equals 90 degree, 180, and 270. If you feed the one at 0 with 0 phase, the one at 90 degree, this is spatial angle with 90 degree phase. The one at 180 with 180 degree phase, you will produce, of course, the calculation I can show it to you. Maybe I think I have a view graph here for the calculations. But if you do it this way, you can prove that in the middle, you have a pure circularly polarized. Again, what is middle? It is some sort of approximation in terms of the frequencies. So you have an area in the middle where the field is really circularly polarized. Or if you have, say, 8 rods, and you feed with 0, 45, 90, and so on. This is one mode. There is another scenario in which you feed with multiple of these angles. In other words, if you have 0, 45 degree spatial, you feed with 0, 90, is double, or with 0, 135, with 3 times. Some equations will show you that all these scenarios are possible for producing circularly polarized field in the middle, because if you consider the whole area, you will never have it exactly circularly polarized. I mean, you have say a circle, and don't ask me how big is this circle. You have this circle, and say in the middle is exactly circularly polarized. You depart the circular polarization slowly, and it is your decision by which % would you like to define the area. If you say, okay, I would like to have, say, up 90%, so you make a line, and this is 90%, and you define this. So it is engineering definition. In other words, there is no sharp definition in which you can say, okay, this area. So high resonance, circularly polarized. Now the problem only the rods will produce that, pure theoretical. But the rods, they need to be connected because I feed the current at certain port and they receive it at another port. So you should connect the ports together with the two rings. The two rings, till now I have a purely inductive structure. Where is the resonance? So I need resonance. How can you get the resonance? Very, very simple. Insert capacitors. The capacitors are inserted. You have also different. This is a real coil here. This is a capacitor here. You can insert here different capacitors here and there. Where, don't forget that you assume that a rod or a piece of wire has a constant current only if the length of this rod or of this piece of wire is much less than the wavelength. If an antenna is also a wire, but you know that the antenna has a current distribution. Why? Because its length becomes comparable to the wavelength. One of the conditions which we need here, we really need constant current distribution. I don't need a rod with, say, half sine wave current distribution. This will not help me in producing the circularly polarized. Therefore, I insert as much capacitors as possible, because between a capacitor and capacitor, you may capacitor is a cut in the current, okay, and if you do some analysis, you can see that it is something like cutting and keeping the current constant. So you insert capacitors, the number of capacitors, whether along the rods or in the ring, it depends on which tolerances do you have. The capacitors must be high quality capacitors, because each losses or each source of losses will degrade the quality factor. So as a whole, you will have a combination of short rods separated by capacitors. Okay? The whole thing is a periodic structure. Okay, this is here for the what is called beard cage coil or whole body coil. Of course, there are some applications, especially as a receiving scenario. The factor that linearly polarized or circularly polarized, this plays an essential role in the transmission scenario, because you pump 1 kilowatt for a short time, of course, and you don't want to lose half of it. But if you ask yourself, do I need the same in the receiving scenario? The answer is not so critical, because you receive very, very weak signal. So you may tolerate the purity of the circular polarization in order to have a less complex form and a more flexible form. Imagine now that you are just imaging the head or the knee, or you are imaging a small animal like a mouse. So for these applications, you have special sort of receiving coils. The main emphasis in receiving coils becomes now a little bit different. In a receiving coil, the main challenge is the extremely weak signal which you receive. You can't imagine which order of magnitude. I can give you just some numbers. For a good system, you have the order of magnitude of minus 110 dBm. A dBm is 1 milliwatt. 110 with minus is 10 to the power minus 11. So you have actually 10 to the power minus 14 received signal. And you can imagine for a given noise level, which challenges do you have? Which signal to noise ratio should you use? It's exactly a communication problem. you know, for those of you who are acquainted with communication, the very first system after the receiving mechanism, after the antenna, should be an amplifier, a low noise amplifier. A low noise amplifier because this dictates the signal to noise ratio for the entire chain afterwards. So in the receiving chain, we have a very, very good, or should have a very, very good LNA. Narrowband, of course, because we would like to minimize noise, and very high amplification in order to see the signal level of minus 110 to minus 120 dBm. So signal to noise ratio is an issue. And this also tells us a whole body Baird cage coil is not suitable at all. Because if you say, I will put my object to be imaged only in the middle in order to guarantee something. So the cage itself will receive from outside. It will not receive signal. It will not receive noise. So in this case, the receiving coils must be as small as possible. In order to say, okay, this is my area which I am imaging. I can illuminate with the big one, no problem. But if I am receiving, I would like to have a compact mechanism, whether it is pure circularly polarized or not, it doesn't play an important role. The main emphasis here, or the main factor here, is very, very high signal to noise ratio. Okay? Therefore, the other variety is what is called surface coil array. And this is actually very, very near to antenna array, as I will explain to you shortly. So in this case, you build coils. So if you look to any coil, so the magnetic field is perpendicular. Maybe it's linearly polarized. And overlapping the coils here is necessary to decrease the coupling, the mutual coupling. Because as an array, as you know from antenna arrays, so the best array has roughly uncoupled elements, because if they are tightly coupled, you can do what you can, and the array pattern itself is not so sensitive to changing the excitation like the case where the different elements are uncoupled together. So this type of overlapping is chosen in order to minimize mutual coupling between the different coils here. And the whole idea here is very, very similar to the work of antenna array. Of course, we work, if we have a 1 Tesla system on 42 megahertz, it is not a microwave, it's in megahertz, but nevertheless, the main theory and the main algorithms we use is similar to the antenna array. Okay, this is here has the advantage if you have surface coils and you say, okay, I would like, this is dedicated to my arm, or this is dedicated to my knee, or to the head. You can build them on a phantom, or which looks like your head, and you have it this way. Okay, this is the second form of the arrays. Okay, this is again, I consider here two identical coils here. Simply, the coils are equipped with the capacitors in order to guarantee high resonance. And high resonance also in the receiving scenario is important for minimizing noise. Because high resonance, you pick up only this part of the noise within your band. Okay? If the two coils are highly coupled, the resonance is split. And in order to reduce the coupling, so you must make it so overlapping in order to reduce coupling. And in this case, you would like to bring all this split split resonances to be very, very near to your Larmor frequency. So this is just the higher the coupling, the wider the splitting of the frequencies. Because if you have a very, very big number, so they will cover a complete range, and this is not good. So we would like to have them resonating at the same. It's something for you maybe like critically coupled and overcoupled and so on, which you learned in electrical theory, electrical circuit. Okay, I will maybe for having some analysis, let us consider this structure. This is here 8-element array. The rods are perpendicular, and let us see which type of field will be excited here. Just to give you a sense how bird cage or how circular array will work. So some equations, I write equations only if they are informative. So I don't write, and this is also an advice for you. If you are presenting, don't write equations which known by yourself only or by this you and your supervisor, thinking that you will impress the audience if you have complex equations. So as a rule of thumb, just present what convey information to the audience. If you have very, very complicated equations like this one here, but I will try to explain it, you think, okay, I am a very, very solid scientist and I can deal with this complicated equation, but you convey a very, very bad message to the audience, because if the audience are not able to understand every individual equation in your view graph, forget it. So you have a certain space, certain time to bring something which is understandable. If they cannot make use of that, so you lost time and you lost part of your presentation. Here I make an exception just to show you that I is the number of the rods. So we have I from 0 to 7 or from 1 to 8. And I will feed them with a multiple of their physical spatial angle. So phi let me check. So phi I is actually, oh, thank you very much. This is very nice for me. So as I told you before, either to say m equals 0. So 0 phase, m is a number of m equals 1, 2, 3, 4, and so on. And phi I for the moment is arbitrary. I will also make what is called small electrical length approximation. As you know, if you have a circuit and the dimensions of the circuit is much less, or the dimensions are much less than the wavelength, you may make some electrostatic approximations. And the length, the real extension of the network itself doesn't play a role. If you draw a circuit and you make your resistance so long, and you analyze it, you don't take into account the physical extension. This is not the case in the microwave, because in the microwave, each individual length, as long as the length is comparable to the wavelength, it plays a role. Okay? The assumption here, k naught times a was the radius, k naught is the wavelength in free space, which is twice pi over lambda. After some analysis, you can, in the polar coordinate system, rho is the radial direction, phi is the azimuthal direction, you can show that the entire field, magnetic field, we are dealing with the magnetic field, in the rho direction, I stay here, so it is the radial direction, is given this way. And important here is to see that you will have a Hankel function. I hope that you still remember what is Hankel function and what is Bessel function. So a Hankel function for the inside radius and a Bessel function for the outside range. And this is the range of phi. Important for me here is what is called the electro or magnetostatic approximation, where k naught rho is too small, which means the physical dimensions are much less than the wavelength, so that you can say I am electrostatic magnetostatic. For this case, you can use the asymptotic value of the Bessel functions coming to this nice form here. I will give you the view graphs afterwards. Important is from all this that if you divide h rho to h phi, the phase difference is j, which is really the condition necessary for circularly polarized field. Okay, so this is j for all values of m, whether you take from here 0, 45, this is m equals 1, 0, 90, 180, this is m equals 2. So whatever you have 8 with angle 0, angle 45, angle 90, 135, and so on. But when you feed with progressive phase, and this progressive phase can equal, for m equals 1, equal the same special angle, or double the special angle, or 3 times the special angle. For all cases, you will guarantee the circularly polarized. I stress on this because we will make use now of what is known in the antenna theory as Butler matrix, just to show you how can we achieve that. Let me take a... Perfect, thank you very much. So just to show you some simulation with, I think it was done by CST or HFSS. This is actually the magnetic field distribution for the circular polarized field. Of course, in a circular polarized field, if you draw the lines for a snapshot, and then you observe the time development of the pictures, you will see it is also rotating with the same. You can prove that because the circular polarization is related. I am staying at a single point and I observe the rotation of the field. But this picture here is a little bit different because you make a snapshot of the field lines at a certain time and then later. So it is you are not staying at a single point. You take the whole cross section. But you can easily prove that for a circularly polarized field, if I'm staying at a single point, the field itself rotates. If I'm taking a snapshot from the field distribution for the whole cross section, the snapshots are also rotating. Okay? Now we come to a known distribution of Bessel functions, just to revive or refresh your information. I need that for my discussion. If you consider the Bessel function first kind, J naught looks like that. Important for me is this area here, because I told you X here plays the role of K naught times A, or the what's called electrical length, twice pi physical length divided by lambda, by the wavelength. Important for me is this one here. If you look here, for G naught, and this is actually what is called fundamental mode, you may have an area where J naught has a horizontal tangent here, where you have, as a distribution of the magnetic field, you have something like the bell. So you have a maximum in the middle, and you have some reduction on the peripherals. And this is what is called fundamental mode of the RF-Coil. And this is again when you feed the rods with phases which are equal to the geometrical phases. 0 is 0, 90 degree with 90 degree phase, and so on. This will create such a distribution, which is something like more or less uniform illumination. Interesting is now G1. In G1, this is the case where you feed with double the geometrical angle. 0 is 0, 45 with 90, 90 with 180, and so on. G2, this distribution here, corresponds when you phase 3 times. 0 is 0, 45 with 135, 90 with 270, and so on. Now try to imagine what will happen now for these higher order modes. The dominant mode is bell, it is G0, with more or less uniform, and the higher order modes, they have a valley, because look to the bezel here, you have a 0 in the middle, and then you go like a hill. The second one has a flatter, more flat valley. Look to G2, and you can also prove that G1 has a first order 0, G2 has a second order 0, G10 has a 10th order 0, by the way, or 9th, which means you have a very, very flat, no field in the middle, and you start to come up at the preference. For lower frequencies, where K0A is small enough, all higher order modes don't play any role. Because if you look here, I'm working here, so the first higher order mode is roughly 0, will not help me. The second higher order mode is still weaker, third, and so on. Only the dominant mode plays a role. And this actually was the case until, say, 10 to 15 years ago, as the strongest or the most powerful MRI system in the market was a 3 Tesla system. 3 Tesla system has a frequency, alarm or frequency of something like 120, because we were talking of 42.6 multiplied by 3, we have 125. It's actually peanut. Starting from 2005, many companies started to produce the first 7 Tesla, and our university was one of the first one ever in Europe to have the 7 Tesla system. The 7 Tesla system, of course, if you raise the strength of B0, you increase the resolution. You can also apply what is called functional MRI. The functional MRI is not for diagnostic. Functional MRI, this is very, very necessary or essential for following biological signals. If I picks you here or you have any pain, so the nerves, they send a signal to the brain, and the brain sends signal back to the muscle to take your hand away. There is a big science in interpreting what happens within our body. Biology, psychology, so you may hear now these interdisciplinary research projects which became now the only projects which are funded. So if you, at least in Europe or in the United States, I spent also some time in the United States, if you apply now for antenna or microwave or something alone, nobody will fund you. Now most of the fund is dedicated to a big collection. So you have 15 universities with 30 institutes, and you have a very, very complex topic like that, in which you have biologists, you have, say, engineers, doctors, and many, many disciplines working in the same area. And one of these examples is the functional MRI. The functional MRI, you would like to see which signal is sent and what happens exactly in a biological process. And for doing that, you need to follow the propagation of this signal, because there are many things which are so fast that you cannot capture them. So imagine that a process which takes place in milliseconds, and your system itself is so lazy that it starts up to take this signal and information after a second. This will happen without having any evidence of what has happened. By the way, one of the Nobel Prize recipients invented what is called femtosecond camera. This was only his achievement. This femtosecond camera is an equipment which shows you processes which starts and ends within a femtosecond. Like if you collide one electron with one positron. So if you don't have the time resolution to observe what's happening, so you see that they disappeared and you have energy. Okay? Or they go, so they don't collide and you see as if nothing has happened. But if you have a high resolution or high speed camera, you can prove that they collide together and each one exploded, bringing many tiny particles which were not known before. And they had some lifetime. They spent alive, they stayed alive for a couple of, say, 10 to the minus 18 seconds, and you don't see anything. And then they recombine again. And now what you see nothing. But what happened is very fast, so that you couldn't catch it. And this is actually many of the modern inventions are very valuable for this reason, that you can follow phenomena which usually cannot be registered using an equipment which is lazy, which is slow. One of these is these processes here. So you would like to see, because the signals are sent very quickly and come back very quickly, and the functional MRI is for that. It is not used for diagnostic because 3 Tesla systems are more than enough for medical diagnostic. But if you have 7 Tesla, nowadays we have research institutes worldwide with 15.4. This is in the United States. And all these are dedicated to functional MRI. Why I tell you that? Because if you raise B naught, you will have additional problems which were not there before. What is the impact of B naught? B naught raises Larmor frequency linearly. The 7 Tesla has something like 280, 300 megahertz. By 300 megahertz, the wavelength is 10 to the power 8 divided by 3 to the power 8. So it's something like 33 centimeters. If I have some powerful one of you, your waist here is more than that. I cannot insert you. I think I'm slim enough to be inserted in 35. But imagine that the physical dimensions of a coil, because you should put the body to be imaged within this coil. You cannot reduce the physical dimension below a certain limit. Of course, as a rule, you can scale down and scale up in the microwaves linearly. If you have a system which is, say, 1 meter diameter at 1 gigahertz, if you raise the frequency to 10 gigahertz, the 1 meter parameters can be reduced to 10 centimeter, and you have exactly the same performance. Because important is the product K naught times dimensions, or twice pi dimension divided by wavelength. But for such application, for some applications, you cannot reduce the physical dimensions below a certain limit, because you are enforced to put your head inside, or you put your arm inside. So in this case, you have to work with the physical dimensions as they are. Now we will create now new problems, because if I have a functioning MRI coil, RF coil at 3 Tesla, either I dimension down to half of its diameter at 7 Tesla or 6 Tesla, or I let it as it is and now deal with the new problems. The new problems will be seen here. And instead of working in K naught in this small area where the G naught is roughly constant and they have uniform distribution, I may extend now to this area, so maybe to 1.5. I'm just giving some examples, it's not typical. So in this case, I have a drop in the illumination, if it is a transmitting coil, and this drop means I don't have a high quality image because the middle is very, very clear. The peripherals are dark. What can we do? If we use now the idea of phased array, what about now, this is my proposal or my suggestion, if we, instead of exciting just the dominant mode, I will excite the dominant mode and the first higher order mode. The middle will not be affected. But I may adjust scale this here so that the sum, say A times G naught plus B times G1 is more uniform than G naught alone. Okay? If I would like to have more degrees of freedom, I will excite this by A naught, A1 and A2. Actually, I have now a number of degrees of freedom which I can play with in order to have the illumination distribution I wish. Okay? Of course, for the very, very simple trivial problem, we would like to have it as uniform as possible over the entire cross section. Maybe 1 or 2 modes are 2 or 3 modes are enough, because just adjust. But imagine now, and this is another area in MRI in which you are working with what is called parallel processing. In the parallel processing, in order to reduce time, you say, instead of repeating the sequence for the entire place, if I need now higher resolution, I must say perform 256 measurements or sequences. What about now of subdividing the area in, say, 16, and I will cover each one of these 16 by just 16 sequences. So I drop the processing time to 1/16. But at the same time, I have 16 processors which catch the information from all these 16 areas, and I reduce the time by 1/16 by parallel processing. I have now more powerful machine, and these powerful machines, they are processing the areas independently. For that purpose, you must take into account if for a single processor is to deal with this area, the other areas should not influence. So I would like for this one to illuminate only this spot. The other one to illuminate only this spot. So each one is illuminated, or each spot. So I subdivide my area in order to reduce time and illuminate them independently. Now the question, do I need for each area a number of coils equal to the number of areas? Because now I'm working independently. The answer is no, because you may use the same coil multiple of times simultaneously. It's exactly like what is called Butler matrix. I don't know how many of you dealt with Butler matrix before. This is called phased array. Because of the linearity of antenna arrays, I can also claim I may produce multiple beams from the same array. One is directed here, and one is directed there, and one is directed there, and one is directed there. They have nothing to do with each other. How? if I have a network before my antenna array and take signal 1 and feed it to the elements in such a way that its beam is directed this way. And I come now with signal 2 and I feed it to the same array elements with another phasing, so that signal number 2 is producing beam in this direction. Signal number 3 will produce phase in this beam in this direction. So now the same array can be used to produce multiple beams, and I can connect different signals with different beams. It's exactly the same idea here. I can because now the array elements are actually here the different no, not the array elements, but the beams themselves are the different distribution here. And the signals themselves is what will be fed to J0, what will be fed to J1, and so on. So actually, I can have a buffer network, which is called Butler matrix. The Butler matrix is a system. The output are the antennas. The input are the signals. So the signal 1 is distributed, say, in phase. So the beam is perpendicular. Signal 2 has a progressive phase, say, with 30 degree. So the beam is 30 degree. 3 is 60 degree, and so on. So the same ideas used for Butler matrix can also be used here. I'm about to finish. I know that Okay, this is here just one example of the Butler matrix. Just for you, Butler matrix is not more than directional couplers and phase shifters. Imagine that this is the antennas. This is the output. We have antenna 1 to antenna 8. And I have here the signals. So if you follow here the signal, this is a 3 dB coupler. So you have here, say, phase 0. And here phase, usually 3 dB couplers, you may have 90 degree phase shift or 180, so depending. And now you have another phase shifter. If you follow this complex structure, you can show that signal 1 is directed maybe to this beam, signal 2 to this beam, so you can produce, this is called 8 by 8, but this number and this number, they are not related. So you may have 3 signals producing 3 beams, but you need the array itself is 8 element array, but producing only 3 beams. Or you may have 5 signals, so producing 5 beams. The array elements may be 100. So you have, in this case, the beams themselves are narrow. Okay, there is another one, and I think this is the last, maybe the, I didn't talk about what's called Rothman length. A Rothman length is equivalent to Butler matrix, but the distribution itself is continuous. Maybe it is not so important here. I can conclude my talk. So we gave an overview on the fundamentals of MRI. I hope that the technical problems of generating these signals has been explained enough. The role of RF coils for producing and receiving the RF field. And the last point was how to make use of antenna ideas and antenna techniques to serve the discipline or the area of MRI. I think I'm done.